In this video, we are going to talk about Stokes' theorem, the second of the three great theorems that would be Green, Stokes, and Gauss, also known, or I often refer to them as the big three. As this topic is probably one of the most involved topics of this course, the review, initially I thought we'd only review the surface integral, but we need a more extensive review. So in my first slide, I am going to do a review of topics that you will need for Stokes' theorem, and also there is one new topic that you will need. And then after that, I will go through a quick overview of this slide and a quick overview of this example, and then we'll go back and take the example in more detail, as well as add a number of additional examples. There are 4 topics that I feel like you need to be really comfortable with in order to work with Stokes' theorem. 3 of them are review, and that would be path integrals, parameterized surfaces, and surface integrals of vector functions. We're going to do a very brief review of these 3. And then this last topic is new, is how to parameterize the boundary of a surface. We will start with path integrals. So if we have some sort of path or curve and we want to integrate a vector function over that curve, we do this in 4 steps. First, we parameterize our path, sigma of t, which will give us an x-coordinate and a y-coordinate dependent on t, our parameter. And just a warning, whenever I talk about paths, I always write sigma of t. Even if the parameter is something like theta, I often label it sigma of t and then I'll have theta in here, so don't be thrown off. Sigma of t is just how I say this is a path. I'll try to be consistent though. Second, write f, our vector field, in terms of the path using function composition because we only are interested of f on the path. So we do f composed of sigma of t. Take the derivative of the path, that's sigma prime of t, which is just x prime of t, y prime of t. And finally, we plug into the interval so that our path integral here will be equal to the integral from a to b, f of sigma of t, our function composition, dotted with our derivative. Our next topic is parameterized surfaces, and we talked about surfaces as thinking of them as something we start off with in a plane, some region in a plane, that then we push and bend until we have this 3-dimensional surface. So the idea is we have this mapping phi, which goes from D, a domain that's in R2, so a subset of the UV plane, in the plane, 2-dimensional, and then we map it to something in 3 dimensions. So phi takes 2 coordinates, u and v, and then it gets mapped to an x, y, and z coordinate in 3 space. Also, uv is what we use in this example. Often we will be using things like theta and r if we're in polar coordinates. So these the parameters may be different for a particular example. We can also calculate tangent vectors. So that's phi, the derivative of phi with respect to v, our second coordinate. So that's derivative of x with respect to v, derivative of y with respect to v, and derivative of z with respect to v. And we can also calculate tu. That's the partial derivative with respect for our first coordinate, dx with respect to u, dy with respect to u, and dz with respect to u. And then our normal vector, the normal to this surface, will be tu cross tv. This topic is new, which is parameterization of the boundary of a surface. So here I have my surface, and I tried to outline the boundary in red. So we want to know how to parameterize that. So what we have to do is go back to our domain, parameterize the boundary of our domain, and then map the boundary using phi over to our 3 space. So the idea of this mapping is it'll map the boundary to a boundary. That's what we're depending on. So we denote this as this delta of our surface. So the boundary of our surface is equal to phi, boundary of our domain. This last topic is review. This is surface integrals of vector functions. So if we want to take the integral of this vector function f over a surface, the steps we do that are 1, parameterize our surface, phi of uv, write f in terms of phi, that is, do the function composition, f composed of phi, calculate the tangent vectors of phi of our surface, and then find the normal to our surface, and then finally plug into our double integral so that our integral of f over a surface is equal to the double integral using our parameterization for our limits of integration for du dv. Then f, this is actually f composed of phi dotted with our normal tu cross tv. A couple of things just to mention is one, often this is the way this formula is written, but you want to remember that this f here is f composed of phi. Another thing is, here you see that we have two paths, and I often call them both sigma of t because that's how I designate a path. But you want to keep sure that you can differentiate both. So I often say that this is sigma of t, and even though I label this sigma t, I also put this ds in front to remind me that it's the boundary of S. We can now turn our attention to Stokes' theorem, which gives us a formula, or gives us a relation between the surface integral of the curl of f. Remember, the curl of f is a vector field. So the surface integral of this curl is equal to this delta s, that's the boundary. So this is the line integral, the integral over the boundary of f dot ds. And this is a lowercase s to designate we're doing a line integral over the boundary of our surface. The best way to get an idea of what's going on is to do a quick example. We'll do it quickly in this overview slide, and we'll go through it in more detail with all the details of integration later on in our video. So the example is to let S be the paraboloid z equals 9 minus x squared minus y squared defined over the disk in the xy plane. Verify Stokes' theorem for the vector field f equals 2z minus y, x plus z, 3x minus 2y. Starting out with our paraboloid, this is our surface we're integrating over. Z equals 9 minus x squared minus y squared. And I have this graph here. It's sort of like the x squared plus y squared would give you that paraboloid, that bowl shape, and the minus kind of turns it upside down with the 9 being on top. So this is kind of our surface here, the paraboloid, and this disk, the circle of radius 3, and the xy plane, so this is what we're talking about, the disk, that's our domain. So this is what gets mapped onto this paraboloid. And we want to verify Stokes' theorem, F, and this is our vector field F. Looking at Stokes' theorem, there's two ways to do this. We want to verify Stokes' theorem. There's two formulas. There's this left-hand side, which is the surface integral of the curl, and there's this right-hand side, which is the boundary. So it's a line integral, the boundary of the surface of f. We're going to start with this left-hand side, which is the curl, and then let's see, since this is a surface integral of a vector field, remember the curl gives you another vector field. Since this is the surface integral of a vector field, we're going to be using this formula here, which tells us how to integrate a vector field over a surface. And that will be, we integrate over the domain that gets mapped to the surface. So integrating over the domain, in the, our domain's in the UV plane, f, and in this case our f is the curl, dotted with TU/TV. Looking at this formula, the first thing I need to do is take the curl. So here I have the curl of my f, which is 2z minus y, x plus z, and 3x minus 2y. And the curl is equal to -3, -1, and 2. And one thing I often do when I'm doing Stokes, and I want to take an integral involving the curl to remind myself not to look here for a vector field, I circle my vector field and I point to the curl. And I talk about that a little more later, but that's just a tip I have for you. When you're doing Stokes, circle your vector field, point to the curl. Looking again at my theorem now. So I'm going to have my curl, which is just -3, -1, 2, dotted with TU cross TV. To get TU cross TV, I need to define my phi, which is my mapping. So this circle here in the plane becomes this surface. And the way it does that is my essentially your mapping is given to you right here, that z equals 9 minus x squared minus y squared. In other words, phi will take an xy coordinate pair and map it into three-dimensional space as xy, and then z is equal to 9 minus x squared minus y squared. We note that x goes between 0 and 3, and then because our domain is a circle, y will go between negative square root of 9 minus x squared and square root of 9 minus x squared, positive square root of 9 minus x squared. I've already noted in this problem that what I'm integrating is the curl of f, which is minus 3, minus 1, minus 2, but sometimes I'm just using this formula in calculating the surface integral of vector functions. So normally my next step then is to do f composed of my phi, and so here I said, well, my f, I composed it with phi, which is xy, 9 minus x squared minus y squared, and this is where I'm looking for an f then to plug in xy and 9 minus x squared minus y squared. So I'm looking for my vector field, and I see that the one I want is my curl. This curl is unusual in that, well, it's not unusual, but it's sort of easy because it's just negative 3, negative 1, 2. All points get mapped to negative 3, negative 1, 2. There are other curls where you'll still have variables x and y's in here, but this one everything gets mapped to negative 3, negative 1, 2. Now I can calculate my tangent vectors. That is first, here I have tu and tv, but my parameters depend on x and y. So tx, the partial derivative with respect to x is going to be 1, 0, and minus 2x. Partial derivative with respect to y is going to be 0, 1, minus 2y. Then my normal is going to be tx minus crossed with ty, which is 2x, 2y, and 1. And then I can plug into my integral. It's my curl dotted with my normal here. And then I use my limits of integration, which are given here. X goes between negative 3 and 3. Y goes between negative square root 9 minus x squared and positive square root 9 minus x squared. I did convert to polar coordinates, so here are my polar coordinates, and then I have to multiply by the Jacobian, and my final answer is 18 pi. Later in the video, I'll give you more details on how this integral was done. But it ends up with 18 pi, and just to remind you, we're integrating the curl, del cross f, over the surface. And it ends up that we're integrating over d, which is an area, and becomes a double integral. As you can see, we have a double integral. Now that we've done this entire integral here, to verify Stokes' theorem, we need to do the same kind of calculation, but using this right-hand side of the equation, that is the integral over the boundary of f ds. And remember, this del s, that's the boundary. And the formula for del s is equal to phi and del of our domain. So in other words, to figure out what del s is, the boundary of s, we look to see what phi does to the boundary of the domain. So the domain here is bounded by the circle 9 equals x squared plus y squared. So we're going to parameterize that boundary of the domain as 3 cosine theta, 3 sine theta. And now if we do phi of our sigma of t, that's going to be, where is our phi? Sorry, I called it phi, but it's actually phi. Or did I write down phi? I must have written down phi here. I have it here. It's our x, y, and our 9 minus x squared minus y squared. So our x coordinate now over here is 3 cosine theta, y is 3 sine theta, and then we have 9 minus x squared minus y squared. So this becomes 0, and finally our path, the boundary of S, or of our surface, is equal to 3 cosine theta, 3 sine theta, 0. So again, this is the boundary of our surface, and I'm going to designate this now as my new sigma of t, because now this is the path when I take this path integral, right? So the boundary on S is essentially just a path. It's a line integral. 3 cosine theta, 3 sine theta, 0. Theta goes between 0 and 2 pi. And the way we do line integrals, if you recall it from our video, We do f composed of our path because we're only worried about f on our path. So we have f plugging in sigma of t. We have 3 cosine theta, 3 sine theta at 0. F now, where our original f is 2z minus y. But z is 0, so minus y will give me minus 3 sine theta. We have x plus z. Z is 0, so we'll have 3 cosine theta, and then 3x minus 2y. So 3 times 3 cosine theta, which is 9 cosine theta, minus 2 times y, which will give me my minus 6 sine theta. Which means now, what else do I need? My sigma prime of t, which will be the derivative of sigma of t, minus 3 sine theta, 3 cosine theta is 0, and I can plug in to my integral. My limits of integration are 0 to pi, my f composed of sigma, my sigma prime, and I get 18 pi, which is the same answer I got using the surface integral. Again, this here is f is integrated over the boundary of the surface. So this is a line integral, and you can see that they both are equal. Because there are so many different types of integrals, I made this chart to kind of organize the information. So here, I basically said there are 2 types of integrals, path integrals and surface integrals. So this row deals with path integrals, this row deals with surface integrals. And then we're either integrating scalar functions, so that's this column, or vector functions, and that's this column. So here, then from there I get the matrix. I write the different steps involved in solving each, the main formula I use, and other notes like maybe physical interpretation and other things. I also have a few notes on Green's theorem, Stokes, and Gauss. I find it really helpful to organize this information. I also have a whole separate video on this chart, on this matrix. I refer to this summary of path and surface integrals quite often, but I often have it in a corner here very small, so you might want to screenshot this so you have access to the full-size version. And I do have a whole separate video devoted to this summary. I should also warn you, when I originally made these videos, it was for my daughter, and at the time I couldn't remember what this phi, this Greek letter, was called. So at the time, it sort of looked like the Green Lantern symbol from, is that Marvel or DC? And so I just called this the lantern. And since I've updated my videos, I've been calling it phi because that's what I believe it is. But just in case, if I forget or if I say lantern, you'll know what I mean. But also warning, no one else calls it the lantern function, so no one else will know what you're talking about if you say the lantern from R2 to R3. Continuing on, there's a physical interpretation of Stokes' theorem. Remember, the curl is related to rotation, so this paddle wheel, it might circle around, but it's not just circling around, it's rotating as it goes. So you can see the arrow, the orientation arrow, the actual disc kind of spins around. So it says the tendency to rotate will vary from point to point, but Stokes' theorem says the collective measure, and the collective measure is this integral over the entire surface, is equal to the tendency of the fluid to circulate around the boundary curve. Here is Stokes' theorem. It's for a parameterized oriented surface. If we have phi that takes a domain in R2 and maps it to a surface in R3, what it says is it relates a surface integral to a line integral. In particular, it says the curl of our vector field integrated over a surface is equal to that vector field integrated over the boundary. That's what this delta S is, the boundary of S. So that would be a line integral over the boundary. I have this drawing of a surface that we will be using later in an example. Here we have the domain. It should be in the XY plane, and it's sort of this oval shape. And then we can map it over into 3 space and get this dome, this upside down bowl shape. And we can either take the surface integral of the curl of the function over this dome, or we can see that that will be equal to the integral, this line integral around the boundary of this surface. Just to remind you how to parameterize the boundary of a surface, it's given here on your summary sheet. So the boundary of a surface is equal to the lantern function of the boundary of the domain. So here you have a surface. It's defined over a domain, that's this yellow portion, but we're only going to look at the boundary of the domain, that's this red circle here. And what we're going to do then, if we parameterize this circle, we will then have something like sigma of theta is equal to cosine theta sine theta because it's a circle. Now we take the function composition of our phi with our parameterization. So that would be phi, and then we plug in sigma, which is 3 cosine theta, 3 sine theta. Now phi, because we get this surface by plotting points x, y, and then for z 9 minus x squared minus y squared, phi is going to be equal to xy 9 minus x squared minus y squared. So when I plug in 3 cosine for x and 3 sine for y, my phi of sigma is going to be 3 cosine x, 3 sine theta, 3 cosine theta, 3 sine theta, and then 9 minus, and I'm going to plug in my x squared and my y squared, which is 9 minus 9 cosine squared minus 9 sine squared. Now I have my parameterization of my boundary, but I'm also going to say it's sort of what you might intuitively think because the boundary is the opening of this circle. But it's good to go through this calculation. A couple of other things I would like to point out. When you take the curl of a vector field, you get another vector field. Remember, the curl produces another vector field. So here, after you've taken the curl, you're still taking the surface integral of a vector field. So this part here, we're in this part of the matrix where we're taking the surface integral of a vector field. It just so happens the vector field is the curl of our original vector field. This over here is a line integral over a vector field. So this part, this calculation here, belongs in this part of the matrix. Last, I have taken this formula here for a surface integral of a vector field, and I've written it here for your reference. For our first example, we are going to go back to that paraboloid, this surface we had seen earlier, and it's defined by z equals 9 minus x squared minus y squared defined over this disk in the xy plane, the disk shaded in yellow. We're going to verify Stokes' theorem for the vector field f equals 2z minus y, x plus z, 3x minus 2y. I just want to point out this definition of disk. In some ways it'll come up a little bit later. But a circle is defined as all the points equidistant from a center point. So if this is our center, then this might be a circle, except that it's not quite right. I didn't draw it quite right. But again, the circle is just the outline here. It doesn't include the points in here because obviously they're not equidistant. Like this point is not equidistant from the center as this point. So the circle is just the outline. The idea of a disk is the disk includes the interior as well as the boundary of a circle. To verify Stokes' theorem, we're going to do the calculations using both sides of this equation, and we'll start with the left-hand side, which is the surface integral of the curl of S. And as I had mentioned before, the curl of F it takes a vector field F, and the curl gives you another vector field. So here, when we take the surface integral of the curl, we're taking the surface integral of a vector field. For that reason, we're going to use this formula here, where our F is equal to is del cross F. So plugging in del cross F here, we get our double integral del cross F dotted with Tu cross TV. The first thing I'm going to do is start with the cross product, which is a good way to start these type of problems, and you'll see even more reason why that's the case with our last example. But to remind you, the cross product, that's just the determinant, so we write the I, J, and K of the del operator, which is d dx, d dy, and d dz, and the last line is just our vector field, so it's 2z minus y, x plus z, and 3x minus 2y. I do the cross product and I end up with -3, -1, 2. Looking at my formula, I have my cross product here, and I need to dot it with TU cross TV. So I'll need to parameterize my curve. Remember, when you have your surface given to you as a function of z of x and y, then the parameterization of your surface is going to be x, y, and then z as a function of x and y. So I complete my parameterization by also specifying the limits on x, and on this circle, x goes from -3 to 3, and then my y-coordinate goes from the minus square root of 9 minus x squared and the positive 9 minus x squared. In other words, the equation of the circle over here. So the next step is to plug in our parameterization of phi into f to do the function composition. So I had done f, and then I wanted to plug in phi, my x, my y, my 9 minus x squared y, and then I was looking for my vector field to put this in, and I saw this. So I started to compose it, 2z, that's 18 minus 2x squared minus y squared, and I was continuing, and then I realized, wait a minute, this is not the vector field that I'm looking for. I should be looking for this one. Because I'm doing this side, I should be doing the curl. So I crossed this out, and also because this is not the first time I've made that mistake, I often, when I'm doing Stokes and I calculate the curl, because I'm doing the left-hand side of the equation over here, once I calculate the curl, I often circle my vector field, and then I put an arrow to my curl, and that will remind me when I'm scanning for a vector function and I see this, the arrow will remind me, oh no, the one I want to integrate is the curl. So this is something I would recommend you do as well. Now when I compose f with phi, I have f of, and then I put in phi, x, y, 9 minus x squared minus y squared, but actually my f, which is my curl, isn't that interesting of a function. It just assigns everything to -3, -1, 2. Now use phi to figure out my tangent vectors. So derivative of phi with respect to x, this would be 1, 0, and then here I have minus 2x. Derivative with respect to y will be 0, 1, and over here I'll have minus 2y. And then to make the normal vector of my surface, I'm going to cross tx with ty, and I get 2x, 2y, and 1. Now I'm ready to set up my double integral. I have my limits of integration for my parameterization. Here I have dy, actually I forgot to write it here, but I wrote it here, and my -3 to 3 goes with my dx, and then I have my curl, right? I have curl, which is over here, -3 minus 2, 2, and then I have dotted with my normal, 2x, 2y, and 1. And I very quickly notice, and you'll see this a lot of the times when you parameterize a circle or something, a surface over a circle, is that these limits might give you some problems later. I did go through the work here so I could show you where it is that I ran into problems. So eventually you plug in your square root of 9 minus x squared, and to integrate this you're going to need some sort of trig substitution, but I don't remember trig substitutions, so I'm going to switch to polar coordinates because we did that just a couple of chapters ago, so I remember how to do that. And I also remember when you switch different coordinate systems, you have to multiply by the Jacobian. So one point is, at any point you can decide you want to convert to polar coordinates. It doesn't have to be at the very beginning. You could have started this in polar coordinates. But I often, when I take the curl, I usually just do it with my f. Like I don't convert and then try to take the curl. So I often start everything in rectangular coordinates until I recognize, oh, I'm going to have problems taking this integral, in which case that's the good time to switch. And again, when you change your coordinate system, you need to multiply by your Jacobian. So here I just noted for you, I'm going to switch to polar, I'm going to multiply by my Jacobian, and my polar coordinates are x equals r cosine theta, y equals r sine theta, my Jacobian is r, and I have that calculation here. The Jacobian is always positive, so it's the magnitude, the absolute value of, and what you do is you take x and you take its gradient. So the partial derivative with respect to theta, which is minus r sine theta, then partial derivative with respect to r. Same thing with y. You take the gradient, and then you take the determinant, so you do the cross multiplication, and you get negative r, but the Jacobian's always positive. Here I have converted my integral into polar coordinates. So I have minus 6, and then I take x is equal to r cosine theta. I have minus 2, y is equal to r sine theta, and then I have plus 2. I also multiply by my Jacobian. Over here, my limits of integration are going to go from 0 to 3, and theta is going from 0 to 2 pi. Now that my integral has been set up, the rest is just integrating and calculations, and my final answer is 18 pi. So I want to remind you, we got this 18 pi by integrating the curl of f over the surface. And when we integrate a vector field over a surface, we essentially do a double integral over the domain. So again, we integrated the curl over the area D, the domain D. For comparison, we're going to do the same calculation, except we're going to use the right-hand side, the line integral side of the equation. I will need the boundary of my surface, and I have this formula here, which is also here on your review sheet under Stokes. So the boundary of the surface is equal to phi of the boundary of the domain. The boundary of the domain, then, is this circle here. So sigma of t is equal to 3 cosine theta, 3 sine theta. So now I need to plug in the boundary of my domain, which is the sigma, into phi. Phi is equal to xy 9 minus x squared minus y squared. So that will be x will be 3 cosine theta, y will be 3 sine theta, then 9 minus x squared, which is 3 squared cosine squared theta, minus y squared, which is minus 3 squared sine squared theta. So I get, for my final answer, simplifying this, which just is 0, I get 3 cosine theta, 3 sine theta, 0. Now, this boundary that I just computed is going to be the curve that I use for my line integral. So I'm just going to rename this boundary as my curve, my sigma of t, from the last slide, which is 3 cosine theta, 3 sine theta, 0. Now I can do my f composed of my curve. And now my f, again, I'm not doing the curl anymore, so I'm going to use my regular vector field, 2z minus y, x plus z, 3x minus 2y. So 2z minus y, z is 0, so I have a minus y, which is minus 3 sine theta. My x plus z, that'll just be x because z is 0, 3 cosine theta, and then 3x minus 2y, that will give me my 9 cosine theta minus 6 sine theta. Next, we take the derivative of our parameterization. So I have this as minus 3 sine x, and this is 3 cosine theta and 0. And then we can plug into our formula. So we're going from 0 to 2 pi. We do the dot product of f composed of phi with our derivative. And the rest is just integration and calculation, and we get the same number, 18 pi. And I wanted to remind you that this 18 pi was found by integrating over the boundary of the surface. So we have completed this task of verifying Stokes' theorem. We've done this integral of the curl over the domain. And again, this was a double integral. It was we were integrating over an area. Here, the other side of the equation, we integrated f over a curve, and that curve was the boundary of the surface, and so we completed a line integral. Our next example is to evaluate this line integral. Here's our vector field f, and we want to integrate over the curve c, where c is the intersection of this cylinder, x squared plus y squared equals 1, and the plane, x plus y plus z equals 1. One of the first things I wanted to do was try to find the intersection so I could figure out what this this curve looks like. And when I first drew it inside, I actually didn't tilt it enough, so it looked like the intersection was more of a parabola. But when I set the two equations equal, the line with the cylinder, I see that I get something more like an ellipse or a circle. It's not going to be exactly like a standard ellipse or circle because there's the tilt. But I definitely see that the x and the y term both have squared terms. So it wasn't a parabola, because a parabola only one would have had the squared term. And then that clued me in that there was something off with my drawing. But for the most part, having the exact equation isn't necessary, as you will see. Since the problem was to use Stokes' theorem to evaluate the line integral, usually that means you're going to use the other side of the equation. If they give you the line integral, you're going to do the curl, the surface integral of the curl. If they say use Stokes' theorem to evaluate the surface integral of the curl, that usually means you're going to do the line integral. And why do I say that? Well, if they just wanted you to do the line integral, they would have said evaluate the line integral. When they say use Stokes' theorem, that means they usually want you to do the other side of the equation. But nevertheless, we're going to do both sides, but we're going to start with the curl. So here I have computed the curl. I put in my function of my vector field f, and then I am taking the determinant with respect to the del operator. And I get 0, 0, 3x squared plus 3y squared. Oh, and here's my lovely drawing of the cylinder intersected with the plane. Anyway, as I had said in my last problem, whenever I realize I'm going to take an integral of the curl, I circle my function f, and I put an arrow to the curl, so I don't forget. I don't try to take a surface integral of f anymore. I'm going to use the curl. Just to get where we are on our summary sheet, so what Stokes' theorem says is we can either take a line integral over the boundary of a surface, and the boundary of a surface is found by mapping the boundary of the domain, or instead of this line integral here around the boundary, we can take a surface integral of the curl. The next step is to parameterize our surface, but looking over here at this drawing, this nicer drawing of this cylinder, the key is to realize that your surface is this oval. Actually, it's this oval here, the intersection. But this intersection is just the part of the plane that we have, the plane that intersects the cylinder. So the plane that we have the equation for up here in the problem statement, x plus y plus z equals 1. It's just this part of the plane, now coming back to my drawing, that's over the domain, and the domain is the circle, the bottom part of the cylinder. So again, it's this oval, but the oval is just the part of the plane that happens to be over the cylinder's base. And actually, it's not just the circle, it's over the whole disk, so I should fill it all in. So I tried to summarize it again over here in writing. The surface is the surface of the plane, but it's only the part of the plane that's over this disk, which is parameterized by x squared plus y squared is less than or equal to 1 in the xy plane. And now I do my function composition of f with my phi, my mapping. So f, and then I plug in phi, which is over here, x, y, and then z is equal to 1 minus x minus y. This comes from my plane. And then my f of x, y, z is not this function, but it's equal to 0, 0, and then 3x squared. In this case, my x coordinate is just x, plus 3y squared, and my y coordinate is just y. I compute my tangent vectors, so my mapping is with respect to x and then with respect to y. So the derivative with respect to x is 1, 0, and minus 1. And with respect to y is 0, 1, and minus 1. And then for the normal, I just cross these two tangent vectors, and I get 1, 1, 1. Now I'm ready to plug into my integral. I have my limits of integration here given by my parameterization. So x on the outside will go from -1 to 1, and y will go from negative square root of 1 minus x to positive square root 1 minus x. Then I need to put in my f composed of my phi, which is equal to 0, 0, 3x squared plus 3y squared, dotted with my normal vector, which is 1, 1, 1. And this is where I'm looking at this 3x squared and 3y squared, and I'm looking at these things that I need to plug in my limits of integration, and I decide I'm going to change the polar coordinates right here. And x is equal to r cosine theta, y is equal to r sine theta, and the Jacobian, like we had calculated in the previous example, is equal to r. Here I have the transformation, so I have 3 and x squared plus y squared will give us r squared, and then I have my r, my extra r's, my Jacobian. My limits of integration now for this circle, here, right, I was parameterizing my circle, which when x went from -1 to 1 and y was the other, using the formula of the circle. So to parameterize the circle, my theta will go between 0 and 2 pi, and now this is a circle of radius 1, so r will go between 0 and 1. The rest is just integration and calculations, and I get 3/2 pi. And we want to compare this if we did the line integral. So again, I had mentioned if you have a problem that says to use Stokes theorem to evaluate a line integral, usually they want you to do the curl, the surface integral of the curl. But just because we're looking at Stokes theorem kind of in more depth than just this one problem, we're going to compare this curl integral to the line integral. I have a small summary of what we did, where we did the surface integral of the curl over here, so we could remember how we did it, and also that our answer was 3/2 pi. Looking at my line integral, so again, we have a vector field and a line integral, so we're in this part of our matrix, and I copied down the formula here. So the next thing we need to do is consider what our curve is. I'm going to use this formula here on my sheet to figure out the boundary of my surface, which will give me the curve. So the boundary of my surface is equal to the lantern function of the boundary of my domain. Again, it's basically you take your boundary of your domain, which is the circle. The domain is the disk. The boundary is the circle. Plug it in to your transformation to get the boundary of the surface, which makes sense because the domain is what becomes the surface under your lantern function. Anyway, so my circle, the boundary, is equal to a disk of radius 1, so that's cosine theta, 1 sine theta, 0 to 2 pi for theta. Then the boundary is going to be the lantern of that parameterization. So the lantern function looks like x, y, 1 minus x minus y. So it's x, which is cosine theta, y, sine theta, and then again 1 minus x minus y. So 1 minus x minus y, which is 1 minus cosine theta minus sine theta. This boundary now is going to become the path for our path integral. So I'm going to relabel the boundary of S as sigma, so now it can fit into this formula nicely. I moved the definition of my path here, and to remind me which sigma it is, I also wrote the ds, so it's the boundary of my surface. It's going to give me my new path for my path integral, and it's equal to cosine theta sine theta 1 minus cosine theta minus sine theta, and I just copied that from the previous slide. Once we have the parameterization of our path, we can plug in, we can do the f composed of our path. So f is minus y cubed, so we have a minus sine cubed theta, x cubed, so cosine cubed theta, and then minus z cubed, so it's this 1 minus cosine theta minus sine theta cubed. And then we can take sigma prime, and then we can set up our integral. This integral, I actually started to integrate. This part isn't too hard. It looks like the worst part, but it's not, because this is just, this part here, the sine theta minus cosine theta, is just the derivative of what's inside here. So that's not too bad. It's the cosine to the fourths. So what you want to do is use your half angle formulas, and after a lot of work, you'll get the answer 3 pi over 2, which agrees with our other method of doing the surface integral of the curl. So again, just to remind you, here we computed the integral as a surface integral of the curl, and this was a double integral over the area, the domain. Whereas here we did the line integral over the actual curve of f. Remember when I said I had one quick example for you? Well, I kind of lied. I have two. So we'll start with this one first. So when I see a question like evaluate this curl, the integral using Stokes, what that means to me is we want to evaluate using the line integral, because if they wanted you just to evaluate this, they would just say evaluate the surface integral of the curl. They wouldn't have to say using Stokes. They could stop there. But in my mind, when they say using Stokes, they're implying you're going to do the other side of the equation. But one thing I am going to say is whenever there's a curl, I often calculate it just to see if it's equal to 0, but it's not. And I will need to calculate the boundary of my domain, but they didn't really tell me what this surface is going to be. But they did give me the equation here of this boundary. So I'm going to use the parameterization of the circle of radius 1, cosine theta, sine theta, 0. And I'm going to add, because I just thought of it, so when you think of the boundary of kind of a bowl, if this is a bowl that's upside down, if someone handed you a bowl and said, where's the boundary, you would probably point to the upper edge of the bowl where you could run your finger around the circle. So that's exactly the sense that I'm using here for the boundary. Once I do that, I can plug in, or I can do my composition, my f of sigma of t. So here's f, I have my y, I have my negative x, and I have my e to the x0, or e to the xz, which gives me 1. I can also calculate my derivative of my sigma prime, and then I'm ready to plug into my integral. And the rest is integration and calculation. This next example is quick. So we have a vector field f here, and we want to show the integral of this vector field around an oriented simple closed curve C, that is the boundary of a surface, is equal to 0. For this, we're going to use Stokes' theorem, and whenever there's any width of something equaling to 0, I often do the curl first. Actually, if you notice all the other previous examples I've done, I calculated the curl pretty early in the game. So here I have my curl is I, j, k, my del function dx, dy, dz, and my vector field f, my y e to the z, x e to the z, and x, y e to the z. I calculate the determinant, and I get 0, 0, 0, which means that our line integral here, since the curl is 0, is equal to 0. And that's it. This problem is done. And because of problems like this, if there's a problem that involves Stokes' theorem, I often calculate the curl early on, hoping to get a 0, and then the problem becomes super easy. But usually that's not the case on an exam. But I'm hopeful anyway. And the other thing, the other big clue that this is going to equal to 0, other than it says it's equal to 0, is they really gave you no information about the simple closed curve, except that it's simple closed and it's a boundary of a surface. So that should tell you that you're really not going to be able to calculate much unless somehow this is either going to be, the curl is going to be 0, or when we get to Gauss's theorem, maybe the divergence is equal to 0. Normally at this point, once we had finished all of our topics and most examples, I would review our overview slide one last time, but I'm going to skip that for now because this video has gotten quite long and we've done quite a few integrals. So we're going to go straight to our review problems. For review, I have this problem for you to try. Let S be the union of two surfaces, S1 and S2. S1 is the cylinder, x squared plus y squared equals 9. And z goes between 0 and 8, and S2 is the hemisphere, x squared plus y squared plus z minus 8 squared is equal to 9 for z greater than 8. And the problem is to use Stokes' theorem to evaluate the curl of f on this surface, where f is equal to y minus 2xy and minus x squared z. So I suggest you graph S1 and S2. You'll see that they share a boundary, and that's important. I haven't shown you an example of that, but I will give you the hint that since they share the boundary, when you use Stokes' theorem to evaluate this, you're going to do, when anyone says, if I don't say, just evaluate this, but use Stokes' theorem, you're going to do the other side, which is the line integral. So since they share a boundary, you're only going to have to do this line integral around the boundary once. I suggest you give the problem a try. Pause the video, give it a try, and when you come back, I have solutions for you. So here's my solution, and as I mentioned, I just moved the boundary. This boundary here that I used is the circle. It's the boundary for both this hemisphere and this cylinder. So I could have plugged in my sigma here, but I would have got the boundary, the same boundary, except at height equals 0. But I wanted to move it up to 8 because it would border both. So this is how I calculated my boundary. The other thing you'll notice, since it said to use Stokes to evaluate this curl, that means I used the other side of the formula, the line integral, which is why I found the boundary, and then I just used my regular line integral, so I don't have the double derivative. It's just a line integral. And is there anything else that I did? Oh, and I did calculate this this curl just because I wanted to see if it equaled to 0, but it didn't. It's not that I used the double integral in the curl. I just wanted to see if it equaled 0. And the other thing, I was calculating my phi's, my mappings, but one, I stopped here because it was going to be difficult. And also I realized since they shared the boundary, I didn't need both phi's. And also I wasn't doing a surface integral. So at some point, to save myself the trouble, I didn't calculate phi of this one. You know, it wouldn't have been that difficult, but it would involve square roots and things. So this is my solution. We covered quite a lot, so thank you for hanging in there with me. But that's it for this video. Thank you for watching.